Download this code from codegive.com, link in the description below. GIS Pipeline Acceleration with Apache Sedona, a comprehensive tutorial. Apache Sedona is a powerful open-source cluster computing system for processing large-scale spatial data. It leverages Spark's distributed computing capabilities to offer efficient spatial data management, indexing, and query processing. This tutorial will guide you through the process of accelerating GIS pipelines using Apache Sedona, covering key concepts, code examples, and optimization strategies. Introduction to Apache Sedona. What is Apache Sedona? Sedona is an extension of Apache Spark specifically designed for spatial data processing. It provides spatial data types. Supports common spatial data types like points, lines, polygons, and multi-geometries. Spatial indexes. Implements R-tree and quad-tree spatial indexes to speed up spatial queries. Spatial SQL functions. Offers a rich set of spatial SQL functions for operations like st_distance, st_contains, st_intersects, st_within, and more. Spatial joins. Enables efficient spatial joins between large data sets. Raster support. Starting with Sedona 1.5, support for GeoTIFF rasters has been added, enabling raster processing and analysis capabilities. Why use Sedona? Scalability. Leverages Spark's distributed computing capabilities to handle massive datasets that are too large for single machine GIS software. Performance. Spatial indexes and optimized spatial operations significantly improve query performance. Integration. Integrates seamlessly with the Spark ecosystem, allowing you to combine spatial data processing with other data analysis tasks. Cost-effective. Open source and free to use, reducing the cost of building and maintaining GIS pipelines. Community support. Backed by a vibrant and active open source community. Key components. Spatial RDD. Represents a distributed collection of spatial objects, geometries. Spatial indexing. Used to accelerate spatial queries by organizing the data in a way that allows for fast searching. Spatial SQL. Allows you to write spatial queries using SQL syntax, making it easier for users familiar with SQL to work with spatial data. Spatial operations. Provides a wide range of spatial functions for manipulating and analyzing spatial data. Join optimization. Includes algorithms for efficiently joining two spatial roads based on spatial relationships. 2. Setting up your environment. Before you start, you'll need to set up your environment with the necessary components. 1. Java Development Kit, JDK. Install JDK 8 or higher. 2. Apache Spark. Download and install Apache Spark, version 3.0 or higher is recommended. Set the Spark_home environment variable to the Spark installation directory. 3. Apache Sedona jar. Download the Sedona jar file from the Maven Central Repository. Choose the version that matches your Spark version and your chosen Sedona backend, core, GeoSpark, GeoTools. For example, if you are using Spark 3.4.1 and want to use the Sedona core backend, you would download a jar file named something like Sedona core 3.4_2.12-1.5.1.jar. The 2.12 refers to the Scala version used to build the library. 4. Sedona SQL jar. Download the Sedona SQL jar, which contains SQL extensions for Sedona. This is often named something like Sedona SQL 3.4_2.12-1.5.1.jar. 5. Hadoop. If you plan to work with data stored in HDFS, you'll need to install and configure Hadoop. 6. IDE, optional, choose an IDE like IntelliJ IDEA or Eclipse for developing your Spark applications. 7. Python, optional if you want to use PySpark with Sedona, make sure you have Python installed. Maven setup, recommended for larger projects. If you're using Maven, add the Sedona dependencies to your pom.xml file. Replace 3.4 and 1.5.1 with your specific Spark and Sedona versions. Important notes about GeoTools ***. GeoTools dependency ** Sedona relies on GeoTools for certain spatial operations. It's crucial to include the GeoTools wrapper dependency. Pay close attention to the version. Older versions of Sedona might require older GeoTools wrappers. The version of GeoTools wrapper listed above is appropriate for recent versions of Sedona, 1.5.0 plus. Check the Sedona documentation to ensure that you are using the correct GeoTools wrapper for your Sedona version. **GeoTools conflicts **GeoTools can sometimes conflict with other libraries in your project. If you encounter conflicts, you might need to exclude specific GeoTools dependencies or use dependency shading techniques. Running Spark Shell with Sedona **. The easiest way to test your setup is to run the Spark Shell with the Sedona jars. Run the following command, replacing the paths to the jars with the actual paths on your system. 3. Loading and creating spatial data. Sedona supports loading spatial data from various formats, including *WKT, well-known text-to-text-based format for representing geometries. *WKB, well-known binary format for representing geometries. *Shapefile *, a popular geospatial vector data format. *GeoJSON *, a JSON-based format for representing geographic features. *CSV/TSV *, comma-separated or tab-separated value files with coordinates. *GeoTIFF *, a raster data format. 1. Loading data from WKT ***. Explanation ***. Import statements ** imports necessary classes from the Sedona and Spark libraries. *Spark session * creates a Spark session, the entry point for Spark applications. *Sedona SQL registrator.register all, Spark, * registers all the Sedona SQL functions, making them available for use in SQL queries. This is essential. *WKT data * a sample sequence of WKT strings. *WKT RDD * creates an RDD from the WKT data. *WKT reader.read, WKT, * uses the WKT reader class from Sedona to parse each WKT string into a geometry object, from the JTS library, which Sedona uses internally. *to df, geometry, * converts the RDD of geometry objects into a data frame with a single column named geometry. * create or replace temp view, geometries, * creates a temporary view named geometries from the data frame, allowing you to query the data using SQL. *spark.sql, select st_area, geometry, from geometries, .show, * demonstrates using a Sedona SQL function, st_area, to calculate the area of each geometry in the geometries view. The .show method displays the results. *spark.stop, * stops the Spark session to release resources. 2. Loading data from shapefile ***. Explanation ***. Spark.read.format, shapefile, .load, shapefile location, * uses the shapefile data source, provided by Sedona SQL, to load the shapefile into a data frame. Make sure to replace path/to/your/shapefile.shop with the actual path to your shapefile. 3. Loading data from GeoJSON***. Explanation ***spark.read.format, GeoJSON.load, GeoJSON location, uses the GeoJSON data source, provided by Sedona SQL, to load the GeoJSON file into a data frame. Replace path/to/your/GeoJSON file.geojson with the actual path to your GeoJSON file. 4. Loading data from CSV/TSV***. When loading spatial data from CSV/TSV files, you'll typically have columns containing the x and y coordinates, or latitude and longitude. You need to create geometry objects from these coordinates. Explanation ***spark.read.csv, CSV location, loads the CSV file into a data frame. **row.getDouble, row.fieldIndex, x, and row.getDouble, row.fieldIndex, y, retrieves the x and y coordinate values from each row. Important replace x and y with the actual column names in your CSV file that contain the coordinates. Also, you might need to use row.getInt or row.getString depending on the data type of your coordinate columns. $s point, $x $y, creates a WKT string representing a point geometry. $WKTReader.read, WKT, converts the WKT string to a geometry object. The code then converts the RDD into a data frame, geometry df, creates a temporary view, points, and demonstrates a spatial query using st_convexel and st_area. 4. Spatial indexing. Spatial indexing is crucial for accelerating spatial queries in large data sets. Sedona provides two main spatial indexing options. **rtree**, a tree-based data structure that recursively partitions space into bounding boxes. Well suited for point data and complex polygons. **quadtree**, a tree-based data structure that recursively divides space into 4 quadrants. Generally faster than rtree for point data but can be less efficient for complex polygons. Indexing with Sedona SQL, recommended. The recommended and easiest way to create spatial indexes is through Sedona SQL. First, you need to load your spatial data into a Spark data frame and register a temporary view, as shown in the previous sections. Explanation ***. 1 set Sedona.global_index equals true * enables the global spatial index. This is essential for spatial joins and significantly improves performance. 2 set Sedona.global_index.index_type equals rtree * specifies the type of spatial index to use, rtree or quadtree. The default is rtree. 3 set Sedona.index.sample_rate equals 0.01 * sets the sample rate for building the global index. A higher sample rate will take longer to build the index but may result in a more accurate index. The sample rate determines the percentage of geometries that are used to build the index. Values between 0.001 and 0.05 are often good starting points. 4. Create global temporary view indexed _geometries as select * from geometries ***. Creating the view triggers the index construction based on the selected index type and sample rate. Indexing with spatial RDD, less common, but useful for custom scenarios. While Sedona SQL-based indexing is generally preferred, you can also create spatial indexes directly on spatial RDD objects. This method gives you more control over the indexing process but is more complex. Explanation *. 1. Spatial RDD. Set spatial RDD, geometry RDD, * create a Sedona spatial RDD from the RDD of geometries. 2. Val quad tripartitioner equals new quad tripartitioner, spatial RDD, number partitions, * creates a quad tripartitioner, which will divide the spatial data into partitions. You can also use S-tier tripartitioner. The number partitions parameter controls the number of partitions. Adjust this based on the size of your data and the number of cores in your Spark cluster. A good rule of thumb is to have 2 to 4 partitions per core. 3. Spatial RDD. Spatial partitioning, quad tripartitioner, * assigns the quad tripartitioner to the spatial RDD. 4. Spatial RDD. Build index, true, * builds the spatial index on each partition. The true argument indicates that the index should be built on the partitioned RDD. Choosing between R-tree and quad tree *. R-tree *. Better for data with varying sizes and shapes, example polygons of different sizes and complexities. * More robust to skewed data distributions. * Generally, a good default choice if you're unsure which index to use. * Quad tree *. Faster for point data. * Can be more efficient if the data is evenly distributed. * May perform poorly if data is clustered in certain areas. V. Spatial queries and operations. Sedona provides a wide range of spatial functions for performing various spatial operations. These functions can be used in SQL queries or directly on spatial RDD objects. Spatial SQL functions *. Here are some commonly used Sedona SQL functions. *st_ contains, geometry 1, geometry 2 returns true if geometry 1 contains geometry 2. *st_intersects, geometry 1, geometry 2 returns true if geometry 1 intersects geometry 2. *st_within, geometry 1, geometry 2 returns true if geometry 1 is completely within geometry 2. *st_distance, geometry 1, geometry 2 returns the distance between geometry 1 and geometry 2. *st_area, geometry returns the area of a polygon. *st_length, geometry returns the length of a line string. *st_centroid, geometry returns the centroid of a geometry. *st_envelope, geometry returns the bounding box of a geometry. *st_buffer, geometry, distance creates a buffer around a geometry. *st_convex geometry computes the convex hull of a geometry. *st_transform, geometry, source_CRS, target_CRS transforms geometry from one coordinate reference system, CRS, to another. Example queries *. Spatial joins *. Spatial joins are a fundamental operation in GIS that involves finding pairs of spatial objects from two datasets that satisfy a certain spatial relationship, example intersects, contains, within. Sedona provides efficient algorithms for performing spatial joins. 6. Optimizing Sedona pipelines. Here are some important tips for optimizing your Sedona pipelines. 1. Global Spatial Index * always enable the Global Spatial Index for spatial joins and distance queries. This is the most significant performance optimization. Use the set sedona.global_index equals true command in SQL or the spatial partitioning and build index methods on spatial roads. 2. Partitioning * choose an appropriate number of partitions for your data. A good starting point is to have 2 to 4 partitions per core in your Spark cluster. The number of partitions controls the level of parallelism in your Spark application. 3. Data locality ** store your data in a format that Spark can efficiently read, example Parquet, ORC. Consider storing the data in HDFS if you are working with a large cluster. 4. Broadcast joins * if one of the datasets involved in a spatial join is small enough to fit in memory, use a broadcast join to improve performance. You can hint to Spark to use a broadcast join using the broadcast keyword in SQL. 5. Predicate pushdown * Sedona can automatically push down spatial predicates, example st_intersects, st_contains, to the data source, reducing the amount of data that needs to be read and processed. Make sure that your data source supports predicate pushdown. 6. Serialization * use efficient serialization formats like cryo to serialize your spatial objects. Configure cryo serialization in your Spark CONF. 7. Memory management * monitor your Spark application's memory usage and adjust the spark.executor.memory and spark.driver.memory settings as needed. 8. Caching * cache frequently used data frames or rows in memory to avoid recomputing them. Use the cache, or persist, methods. However, be mindful of memory usage. 9. Reduce data volume early * perform data filtering and aggregation operations as early as possible in your pipeline to reduce the amount of data that needs to be processed. 10. Exploit vectorization * in certain cases, converting your spatial data to vectorized representations can improve performance, especially for raster processing tasks. 7. Example GIS pipeline. Here's a more complete example of a GIS pipeline using Apache Sedona. Explanation * 1. Load data * loads point data from a CSV file and polygon data from a shape file. 2. Create geometry columns * creates geometry columns in the data frames using wktreader.read, 4 points, and automatically when loading a shape file. 3. Set global index parameters * enable global index and set the index type to artree. 4. Create indexed views * create a global indexed views to trigger the index construction. 5. Spatial join * performs a spatial join to find points within polygons using st_contains. 6. Aggregate * aggregates the results to count the number of points within each polygon. 7. Buffer and save * buffers each point by a specified distance. Saves the buffered geometries to a shapefile using datasync.write.format, shapefile. 8. Stop Spark session * closes the Spark session. 8. Raster data support. Sedona 1.5 and later versions added support for GeoTIFF rasters. Loading and processing GeoTIFF data *. Explanation * 1. Load raster data * the spark.read.format, geotif.load, raster path, statement loads the GeoTIFF file into a data frame. The geotif data source is provided by Sedona. 2. st_metadata, raster, * retrieves metadata about the raster, example width, height, number of bands, CRS. 3. st_tile, raster, geometry, * extracts a tile, subset, from the raster based on a specified geometry. This is useful for processing only the relevant part of the raster. 4. st_reproject, raster, source_CRS, target_CRS, * reprojects the raster from one coordinate reference system, CRS, to another. 5. st_value, raster, geometry, * retrieves the pixel values from the raster that fall within a specified geometry. Important notes for raster data asterisk. Asterisk GeoTools version compatibility asterisk as with vector data, ensure that your GeoTools version is compatible with the Sedona version you are using. Asterisk memory considerations asterisk raster data can be large, so be mindful of memory usage when processing rasters. Asterisk performance asterisk raster operations can be computationally intensive. Optimizations like spatial indexing, where applicable, and partitioning are important. Asterisk limitations asterisk support for raster operations in Sedona is still evolving, and some advanced raster analysis functionalities might not yet be available. 9. Conclusion. Apache Sedona provides a powerful and scalable platform for accelerating GIS pipelines. By leveraging Spark's distributed computing capabilities and Sedona's spatial indexing and SQL functions, you can process large-scale spatial data efficiently and cost-effectively. Remember to focus on spatial indexing, data partitioning, and memory management to optimize your pipelines for maximum performance. This tutorial provides a solid foundation for building and deploying sophisticated GIS applications using Apache Sedona. As Sedona continues to evolve, expect more advanced spatial analysis capabilities and performance enhancements in future releases. Always